Greetings, folks. So, we're dealing with rotational motion. We've done a little bit with kinematics. We're now ready to start dealing with Newton's second law. The rotational counterpart to force is torque. The easiest kind of torque-related problem that you could run into are what are called rigid body problems. In a rigid body problem, you have an object that's sitting in equilibrium. What that means is that if you sum up the torques about any point at all, the sum of the torques has to equal zero. For that matter, the sum of the forces in any particular direction have to equal to zero because the body's in equilibrium. The rigid body problem that I used to do was a beam. I had a 6-foot beam that was pinned at one end. I used 4 or 5 kilograms of mass that was hung. There was a cable attached to the beam. I had students standing up on tables, holding on to the cable with a huge spring balance, making measurements, measuring angles with a protractor, and it was really quite a wild thing to behold. With the advent of computers, things needed to become a little more petite, so I built a device. This is the base of the device, so I've got eyelets here through which a pin will go. I have a beam here, so the beam has a hole through which the pin will go. There's an eyelet here that a string will be attached to. There's an eyelet here that a hanging mast will be attached to. So I have this set up pretty much ready to go. I have a force transducer here. I've calibrated the force transducer, and then in putting it into the position that it is, I've zeroed it. I have my pin. I'm going to take the pin and put it through like so. So I now have my beam pinned and ready to fly. There's a string here which you can't see, but it's here. I'm going to need to orient this thing so that the string going through the eyelet is such that the string is coming off of the force transducer at right angles to the force transducer. So the way that the force transducer works is if you pull on it or push on it along the line of the little nubbin that's coming out, you will register force. If you push or pull at an angle, you won't get the full force. So I need to have the string coming right straight out, which means I need to manipulate this thing in such a way that I get it so that, as best I can tell from eyeballing it, the string is coming right straight out. Now, as I said, you can't really see in the video whether or not I've done the job here, but I can tell you that I pretty much have. So once I get the length of the string that's appropriate, what I normally do is I detach and I make a loop which makes the actual length of the string just the right length. So when I hook the string up, I can let it go. The string will be coming off appropriately, and it will be holding my beam. I need to know what the force is in the string, and I have a computer set up. The information is going into the computer, and I can let you see that. So the computer is reading 3.19 newtons. That's how big the force is that's being applied via the string. We're going to need to know what this angle is right here. So if I were to take my cell phone, I'm using an app that will measure angles. As soon as I find it, I'm going to zero it with the horizontal. Okay, so if I were to go ahead and go from here to here, I will measure an angle. If I go from here down to here, I will measure the same angle. So this angle right here, I will show you. It's 19 degrees. That seems to be the measurement that it's taking. And then the other angle we really need this angle right here, but the best I can do is to go from the horizontal up. So I know that this angle is 19 degrees. If I can get this angle, I can add whatever this angle is to 19 degrees to get this overall angle. To get this angle, I'm simply going to go ahead and put the measurement along this line here. And it seems to be measuring 26 degrees, 27 degrees. 27 degrees. So a little iffy on the measurement. I'm moving around a little bit, but 27 degrees seems to be a good approximation. So we now have the force. We know the angle is 27 degrees from the horizontal up. We know the angle here is 19 degrees, which is the same as from the horizontal down. And the only other bit of information we need is how big the force is if I go ahead and put 500 grams on the outside here. At least the only other bit of information we need as far as forces go. So I'm going to go ahead and put that on. I need to look to see, make sure that this is still pretty much aligned, and it pretty much is. And we're going to go over and look to see what the tension of the line now is, and it looks to be about 13, I don't know, say 13.7. It's kind of bouncing around a little bit, but we'll say it's 13.7. So the last bits of information we need are actual lengths. So we need to know the distance from this axis out to where the tension is effectively acting. And I'm going to assume that it's acting along a line that goes through the central axis. So it's going to be a distance like so. And I'm going to call that L sub t. And I'm going to make that measurement. I'm going to make that measurement here. And I actually made the measurement earlier, but I can see that it's coming out to be approximately what I made before. And that value is 0.353 meters. I need to know what the distance is to where the 500 grams was acting as it passed through the central axis. And effectively, that's pretty much right to the edge. So I needed to measure from here out to here, like so. And when I made that measurement earlier, I came out to be 0.587 meters. And then I needed to figure out what the distance was between the pin and the center of mass. And to figure out the center of mass, I did the old balancing act. So apparently the center of mass is like right about there, give or take. And then because I had some mass lapping over here, I actually fudged by just a hair. But when I made that measurement, I came out with 0.287 meters. And then the last two bits of information that you needed was the hanging mass. You needed to know how big it was, and it was a ½ kilogram, so it was 0.5 kilograms. And you also need to know what the mass of the beam is. The mass of the beam is 0.314 kilograms. So if I go ahead and put in all of that information, I guess I should write it all down, which I guess I can do. And we have a tension force of 3.19 newtons without the 0.5 kilogram mass, and a tension force of 13.7 newtons with the 0.5 kilogram mass. So our values, our data, looks like this. And that's it. Have fun with the write-up.